Hello, my name is Jürgen Bengorovsky and I want to tell you something about an experiment that we did last year to pave the way for the quantum internet. We did this experiment at the University of Bristol in cooperation with the ICORCI Vienna and the CEMS Photonics at RBI Zagreb. What do you need this quantum internet for? There's a lot of answers to this question, but in our case our research is focused on security. You can use quantum physics as a resource to relay unconditionally secure messages.
Unconditionally secure really means that the laws of physics guarantee that no eavesdropper, no adversary can listen in on your conversation. However, so far, most experimental implementations have focused on two communicating partners only. Traditionally, we call them Alice and Bob. So it's just the two of them talking to each other in a secure way, but an internet with only two participants doesn't sound very exciting. And what can you do if you want to include more participants? Let's say Chloe here also wants to join the secure quantum network. Well, one obvious choice is to just establish another connection between Bob and Chloe. And then, if Alice wants to talk to Chloe, she needs to relay her message via Bob. But this, of course, means that Bob needs to be trusted. He's a so-called trusted node. And this is actually a rather strong limitation on security, because what if Alice doesn't even know Bob or just doesn't trust him? So, to make really unconditionally secure communication between Alice and Chloe possible, you would need another direct connection. But as you can imagine, these connections, they become a mess pretty fast if you include more and more participants. So let's say Dave here also wants to join the network. Then you already have 1, 2, 3, 4, 5, and 6 connections. And as you can see here already, the number of connections actually grows much faster than the number of participants. So I'm too lazy to draw this, but for 10 people, you need 45 connections already. And for 100, it's even 5,000. Now imagine if each of these connections needed separate hardware. And that is the typical state of quantum communication as of now. Our network is here to change that. And the solution comes in the form of quantum entanglement. Instead of now connecting each and every user with each other and with one direct connection, we came up with a scheme that only requires one glass fiber per user connected to a source of photonic entanglement. So instead of this mess, you have a nice star topology. If you look at this now, you could however ask, well, but isn't this source now the trusted node, just like Bob was before in the communication between Alice and Chloe? But thanks to quantum physics, the answer is no. The photons that are sent, thanks to the laws of quantum mechanics, leave no information at the source behind. Using only one fiber per user is a huge cost saver and makes the implementation much simpler. In our case, we fully connected 8 users using only 8 fiber connections instead of 28. We did this by combining several multiplexing techniques, which makes the network easily scalable, enabling larger and larger individual quantum networks. So our scheme is actually expandable to many new users. And the cool thing is that each user just needs one more glass fiber and his detection equipment. We have demonstrated this scheme on deployed glass fibers around the city of Bristol. After careful adjustment of the quantum service provider, the scheme ran smoothly over many hours without any automatic or manual intervention. This demonstrates an important step towards quantum cryptography with many users, which is an essential requirement for our vision of a global quantum internet.